Big Bang Theory describes the birth, evolution, and fate of the universe. According to it, the universe was extremely hot, supermassive state that expanded rapidly in all directions. And you have to note that prior to Big Bang, there was nothing. There was no time, no matter, thus no universe. And it was said that the expansion began approximately 13.7 billion years ago. Our universe began with an explosion of space itself, the Big Bang. Starting from the extremely high density and temperature, space expanded, the universe cooled, and the simplest elements formed. Gravity gradually drew matter together to form the first stars and the first galaxies. But how can we account the Big Bang to the creation of the first elements? How were the first elements formed? Hydrogen and helium formed when the universe had cooled enough to allow their nuclei to capture electrons. It was during the first 3 minutes following the Big Bang, hydrogen and helium were formed as the universe began to cool enough for the protons and neutrons to form hydrogen nuclei. Stars were formed when gravity causes clouds of interstellar gas and dust to contract. This now leads us to the evolution or the life cycle of stars. Did you know that the stars we see visibly during nighttime was once born and will one day die? Yes, you have heard it right. Stars do form and evolve during their lifetime. Stars can be classified whether a low-mass star or a high-mass star. The birth of a star begins with the gathering of hydrogen in large packets of cold gas and dust within enormous interstellar molecular clouds. The gathering of these materials is due to the gravitational attraction. Now, as the interstellar mass condenses and loses gravitational potential energy, the temperature rises and the material gains thermal energy, and it becomes what is known as a protostar. As the protostar continues to decrease in size, the temperature continues to increase, and a thermonuclear reaction, also called fusion, begins in which hydrogen is converted into helium. A protostar becomes a star as it moves on to the main sequence at a position determined by its temperature and brightness, both of which depend ultimately on its mass. The star continues to fuse hydrogen into helium. The lifetime on the main sequence for a star such as the Sun is about 10 billion years, and the Sun has been there for about 5 billion years so far. As hydrogen in a star's core is converted into helium, the core begins to contract and heat up. This heats the surrounding shell of hydrogen and causes the fusion of the hydrogen in the shell to proceed more rapidly. The rapid release of energy upsets the pressure-gravity force balance, or the hydrostatic equilibrium, and causes the star to expand, cool down, and enter the red giant phase as it moves off the main sequence. Eventually, the core of a red giant gets so hot that helium can fuse into carbon, and if the star's mass is great enough, other nuclear reactions soon occur in which heavier nuclei may be created. During the red giant phase, a star varies in temperature and brightness. It becomes a variable star for a relatively short time. The star becomes very unstable and the outer layers are blown off, forming a beautiful planetary nebula. Now, a planetary nebula, the name may sound as it is more of a planet than a star, but that is not the case. Rather, it is a ring-shaped nebula formed by an expanding shell of gas around an aging star. The remaining core of the Planetary Nebula is now a white dwarf, in which fusion no longer occurs, and the star slowly radiates its residual energy into space as it cools. When a star becomes a white dwarf, it gets very small. It has gravitationally collapsed to the smallest possible size, where the force of gravity is offset by the repulsive force of the electrons in each atom. Such is the life cycle of a luminous star: protostar, main sequence star, red giant, planetary nebula, and finally a white dwarf. Now moving on to the life cycle of high-mass stars, they form in the same way as all other stars, but they become red supergiant after they move off the main sequence, and they eventually explode as a type 2 supernova, leaving behind either a neutron star or black hole. Nova or new star is a star that appears dim. It is a result of a nuclear explosion on the surface of a white dwarf. A nova is not literally a new star, but a faint white dwarf that temporarily increases in brightness. The creation of element is known as nucleosynthesis. Nucleosynthesis is a theory that explains the formation of the chemical elements. It is identified in three cosmological events: Big Bang, star, and supernova. During the Big Bang, the first two elements formed were hydrogen and helium. Now let's look at first the formation of a helium. There are actually three steps for the formation of helium that I'm going to discuss. Now let's look at the first step first. For the first step of helium, we have two sets of neutron and proton interacting with one another. When a neutron and a proton interact with one another, they create Deuteron. Now below here, there is an interaction of a neutron and a proton, and the energy is ejected. Now, of course, we have Deuteron as a result. So take note that in the first step, an interaction between neutron and proton creates a deuteron. Now let's have the second step. Say that in the first step, we already have two deuteron. Now when these two deuteron interact with one another, they form helium-3 with two protons and one neutron. You have to note that when two deuteron interact with one another, they create helium-3, but they eject one neutron. So in the second step, to summarize it, two deuteron interact with one another. And you have to take note that one neutron gets ejected as helium-3 is being formed. Now for the third step, say we have already a helium-3. When this helium-3 interacts with one deuteron, it creates helium-4. Now in this step, one proton gets ejected. So in the third step, the summary would be an interaction of helium-3 and deuteron, and one proton gets ejected and helium-4 is formed. Now it may be overwhelming to memorize all the steps, but in summary, we can just write it as one neutron plus one proton that equates to a deuteron. When two neutron and one proton interacts, that is tritium. While when there is a one neutron with two protons, we have helium-3. And when two neutron and two proton interacts, we have helium-4. On the other hand, hydrogen forms when a proton attracts an electron to revolve around it. So this proton attracts an electron. But initially, there were only few hydrogen atoms created because the electrons were moving so fast due to the very high temperature. But as the temperature drops down, the electron is slowed down and the protons had a higher chance to attract electrons. Since the process of forming hydrogen atom is simple, the hydrogen atom is the most abundant element in the universe. Now to achieve more stability, hydrogen atom clumps up with another hydrogen atom, resulting into a hydrogen molecule, or what we call the H2 molecule. And for a stellar nucleosynthesis or a star nucleosynthesis, this occurs during the formation of protostar. Now, the first stage in every stellar nucleosynthesis for every star is what we call the hydrogen burning. What happens in the hydrogen burning stage in a stellar nucleosynthesis is that the hydrogen is converted into helium because the hydrogen gets burned. Now, this is the case for a low mass star. For a low mass star, we have what we call a PPI or a proton interaction. This reaction actually takes place during the hydrogen burning. So, in other words, we can say that the PPI or the proton-proton interaction creates a new inner core that is made up of helium. So, the PPI interaction is what actually creates a helium core in a star. Now, as the helium is constantly burning now, this time we move to a helium core. So, the star now has a helium core. Now, as this helium continuously contracts as it burns, so the helium core continuously contracts and burns, we create another core that is what we call carbon core with some oxygen. So, when the helium core burns or contracts, another core is created. The new core is called the carbon core. Now, what process is required for a helium core to move into a carbon core? We call that the Tripol alpha process. So, this is the process or reaction that is required for a helium core be converted into a carbon core. We call it the triple alpha process. Now, as low mass star burns up its core and use up its fuel, so when a star burns up its hydrogen and then its helium and then its carbon core, that's when the time that this star would die because it used up its fuel and thus it becomes a planetary nebula. Now, this planetary nebula would then turn into a white dwarf, which is the final stage or the last stage of a low mass star. This now would be the final destination of a star or of a low mass star. Now, on the other hand, we have a formation of high mass star. For a high mass star, still the first process or the first stage would be the burning of hydrogen because basically all other stars is made up of basic elements, hydrogen and helium. So the first stage would still be hydrogen burning. But the difference of a high mass star and a low mass star in the stage of hydrogen burning is the process that takes place. So for the low mass star, we have said that a proton-proton interaction process or reaction is required for hydrogen to burn in the case of low mass star. In the case of high mass star, a cycle CNO or the carbon, nitrogen, oxygen cycle is what actually takes place. Now, carbon-nitrogen cycle is also called the CNNO bicycle or the carbon-nitrogen-oxygen bicycle. Now, this reaction takes place in burning the hydrogen in a high-mass star. And for a high-mass star, the reaction does not stop with carbon core. So, in a low-mass star, if you remember, I have said that it ends up in a carbon core. So, when a low-mass star has already a carbon core, the low-mass star would eventually use up its fuel and then it would die. But for high-mass star, it doesn't stop when it has a carbon core. It would go further into having an iron core. Now, once iron core is created, so when the high-mass star already creates an iron core, there is no longer any nuclear reactions that will follow. Why? Because iron is the most stable element based on its mass per nuclear ratio. So that's the difference between low mass star formation and high mass star formation. Now we proceed to what we call the supernova nucleosynthesis. Supernova nucleosynthesis actually creates heavier elements. So what do we mean by heavier elements? Of course, the elements heavier than iron. So any elements heavier than iron is created during the supernova. But what is supernova? Supernova is the explosion of a high mass star. Those are the three ways or three identified categories were under nucleosynthesis. We have Bigbang, star or stellar, and then the supernova. So remember that in Big Bang, we create light elements. We have the hydrogen and helium. And for stellar nucleosynthesis, we start from carbon to iron. And then for supernova, we have the heavier elements being created. Those basically how light elements form and heavy elements form during the life cycle of a star.